Hi, welcome back to my channel. This is episode 3, and I'm continuing investigating if the HackRF, this device here, can be used as a spectrum analyzer. So this was, I explored a little bit this possibility in episode 1, and yeah, it worked quite well. And then I say that it might be interesting to check out how the precision in terms of power response of the spectrum analyzer of the HackRF, to use the tracking generator functionality of my HP 8591E spectrum analyzer to check the precision of the HackRF. So in episode 2 I explain how the tracking generator functionality works in my HP here. And currently the HP is sweeping, so the center frequency is 10 megahertz, the span is 18 megahertz. So the sweep process goes from 1 megahertz to 19 megahertz. Okay. Currently the tracking generator is connected from here to my oscilloscope channel 1. And I can now go into here, activate the tracking generator. So I'm going to click this button. And the tracking generator, as you can see, will output minus 10 dBm of power. So let's see how it works. So indeed it's outputting a signal, and the frequency, as you can see, is increasing following the sweeping process. As we discussed in episode 2, here we have the signal is having about 2 divisions up and 2 divisions down. Currently the vertical resolution is set at 50 millivolts per division, so we have about 100 millivolts up and minus 100 millivolts down. And as we saw in the previous episode, if we go to this utility provided by Analog Devices in their website, and if we write minus 10 dBm, we indeed see that the signal should have 100 millivolts or 0.1 volts peak to peak, which is exactly what we see on the scope. Okay, so now my goal is to connect this tracking generator to the HackRF to probe its response from 1 MHz to 1.8 GHz, which is the limit of this tracking generator. There is a little problem though. The fact is that the HackRF 1, if you go to the official Wikipedia page here, it's very sensitive. So the maximum power you can put in it as a receive in the receive mode is minus 5 dBm. Okay. So the moment, the tracking generator is going to output minus 10 dBm, so everything should be fine. But just to be completely safe, I think it's better to inline 10 dB attenuator in this line of output of the tracking generator. So this will reduce the power from minus 10 to minus 20, and that's going to be safe for the HackRF. So let's see how this works. So I'm going to turn off the tracking generator for a second. So I'm getting the output here, and I'm adding this attenuator. Okay, it's done. Now if I reactivate the tracking generator here, the output is still set at minus 10 dBm. So but of course the signal is, as expected, is lower than that. So in fact, let me increase the vertical resolution. The moment it is set to 10 millivolts per division, and the signal is about 3 divisions, so 30 millivolts peak to peak. And indeed, if we go to the utilities software here, and we write minus 20, which is what we are expecting to see, we get exactly that the signal is supposed to have 30 millivolts peak to peak, which is what we get on the scope. So indeed now we are outputting minus 20 dBm out of the tracking generator. That is going to go into the HackRF. Okay, so I'm going to turn off the tracking generator again. So take it out. I'm going to remove this BNC adapter that was put here to connect to the scope, which has a a BNC connection, and I'm going to plug it into the HackRF. Okay, so I think it's not a great practice actually to connect directly the antenna to the HackRF while the power is on. So I read online that you risk to fry it, so be careful. I'm doing it, but I should really not. And okay, now if I go to the terminal now of my Linux system and I write the command HackRF info, I see that the HackRF is up and running, so everything is recognized. The HackRF is recognized by the system. So I'm now going to so let me actually move this window here over here. We're not going to need the oscilloscope anymore, and let me get the QSpectrumAnalyzer application. So that gives the HackRF spectrum analyzer functionality. Okay, and you can still see the output, I mean the interface, the display of my HP spectrum analyzer here. So I'm going to I'm going to set the tracking generator to output from 1 MHz to 1.8 GHz. So to do that, I go to frequency, and the center frequency is going to be set at 900 MHz. And the span, we put it 1.8 gigahertz. Okay. As you can see, the sweep time now is set to 30 seconds. So it's going to take about 30 seconds to the HP to span the entire band from 0, in reality is 9 kilohertz, to 1.8 gigahertz. Okay. Now, before activating the tracking generator and seeing the response there on the output of the, I mean on the HackRF, let me start the HackRF functionality. I hope you can see it. I hope it's visible enough. So let me see if I can increase it slightly. So still maintaining visibility over the buttons of the HP here. Anyway. So if I activate now the spectrum analysis on the HackRF, let's do that. It works. So currently there is no signal being outputted by the spectrum analyzer because the tracking generator is currently off. So the HackRF reads this output. So as you can see, all the signals that we see here are fake. They do not exist. In particular, we see very clearly this 1.2 gigahertz signal that doesn't exist. We discovered this in episode number 1. And there are other signals as well. So this is a simple way to see what artifacts the HackRF produces as a spectrum analyzer. Okay. Currently the QSpectrumAnalyzer is set to average, but let's see the main curve. So this is the real-time view of the spectrum produced by QSpectrumAnalyzer utility. And let me remove the average. In fact, I will add a max hold, which takes the peaks. Okay, so that's the red line, or I don't know if it is displayed in blue for some reasons in this screen capture, but anyway. Right, so we are now ready to activate the output of the tracking generator. So I'm going to do just that. So let me go to tracking generator and start it. So as you can see, quite clearly, the QSpectrumAnalyzer is following the signal produced by the tracking generator. And so what I wanted to check with this test is the response. So you know, the response actually appears to be very flat across all the spectrum, which means that HackRF is very good in this respect. I was expecting a much less flat response. And if we go here, we see that it says about -10 dBm. So as we know, this is wrong because currently the wait a second, I see there is some kind of problem because I'm reading on the spectrum analyzer tracking generator on level. So this means that the tracking generator cannot sustain its tracking activity, so its output activity across all the spectrum. Let me see why that might be the case. So let me stop it for a sec. And I'm going to change the span to just 1.7 gigahertz, just to see if the problem was caused by the initial activity on the spectrum analyzer from 0 to 100 kilohertz, where the tracking generator cannot produce its output. So let's see. So the span is now set to 1.7 gigahertz. It means that now the initial point will be about 50 megahertz. So let me start again with the tracking generator. And okay, now let's start it. Okay, so now it's working, and as you can see, we get no error message from the spectrum analyzer. So yes, indeed, that message was caused by the fact that at the very beginning, so from 0 to 100 kilohertz, the spectrum analyzer was sweeping that area because it was set to start from 0 hertz, but it could not really output the desired frequency because this tracking generator is limited and can only start at 100 kilohertz. So setting a smaller span solved the problem. Anyways, let's go back to QSpectrumAnalyzer here. And as you can see, yes, we get this nice response, which is pretty flat. And it's clearly following the tracking generator. And the fact is that it's saying that the power here is at minus 10 dB. So fact here is that it says dB, it doesn't say dBm. So it's a relative notion of power. And we know that this level is in fact minus 20 dBm. So minus 10 dB read in a QSpectrumAnalyzer in fact means minus 20 dBm. So let's try to change the power of the tracking generator. So I'm going here, and I'm going now to change it to minus 20 dBm, just to try. So minus 20 dBm. Right. And now you see indeed that the signal has decreased. It's now so let's remove the max hold for a sec and reactivate it. Oh, max hold. So perhaps I should stop and restart. That's going to be simpler. Right. So now, as you can see, the level is at minus. It's written here. It's about minus 20 dBm. So which is compatible with the previous reading. So the previous reading we had minus 10 dB corresponding to minus 20 dBm. Now we have minus 20 dB read on QSpectrumAnalyzer, and that corresponds to minus 30 dBm because the spectrum analyzer is outputting minus 20 dBm, but we also have 10 dB of attenuation, so that's minus 30. So the response is quite linear in this respect. So let's check out also minus 30 dBm on the spectrum analyzer. So I'm going to do that. Okay. So let me stop here and start again so we can follow. And here it is at minus 30. So it's very linear. It's basically the conversion appears to be quite simple. So the reference level here is basically 10 dB means minus 20 dBm, 20 dB means minus 30 dBm, and so on. So let's try to go much lower. So for example, to see if this is consistent, so minus 50 dBm. So again, stop and start. So we expect here a minus 40 dB reading, and minus 50, sorry, yeah, because here we are outputting, this kind of stopped for some reason. So we are reading minus 50, which is correct, yes, because the spectrum analyzer is outputting at minus 50 dBm, but we also have a 10 dB of attenuation, so the signal is really minus 60 dB. And here we are reading that value plus 10 dB basically, so which is pretty good. As you can see, the response is starting to be a slightly less flat around high frequencies, but it's still very good. So I would say that I'm very pleased by the response of this HackRF in terms of consistency and flatness across the spectrum. So I think this really can be used as a decent, simple but decent spectrum analyzer. So let me turn off completely the tracking generator once again. Stop and start again here, and again show the average. So that shows the only problems that this device has as a spectrum analyzer, at least in the range that I could test 0 to 1.8 gigahertz. Yeah, is that it has these imaginary signals, these spurious signals that are generated by the HackRF itself and then do not exist in reality. So anyway, once you take these under consideration, and anyway they are pretty low, well, this one is the highest one. It's at 20 megahertz and it says minus 34 dB. Okay, which we know it corresponds to a reading of actually minus 44 dBm, and so it's pretty low. And this is a signalet that we already encounter at 1.2 gigahertz at minus 42 dB, which corresponds in reality to minus 52 dBm. So once you know and the others are very low, you see. So once you know this, you can use the HackRF, I think, pretty reliably as a spectrum analyzer, and that's a very great thing because the HackRF costs very little actually, and about $100 included the enclosure. So it's a really great gadget. So thank you very much, and if you like the video, of course, feel free to comment and suggest some improvements on the analysis, and or to subscribe. Thank you. Bye.